The student raised his hand in the back of the lecture hall. Richard Feynman had just finished explaining quantum electrodynamics using nothing but chalk and his hands. "Professor, I have a question about something simpler." Feynman smiled. "Simple questions are often the hardest ones. Go ahead. Why does fire burn?" The room went quiet. 200 students waited. It seemed like such a basic question. Everyone knew fire burned. That's what fire did. Feynman didn't answer immediately. He walked to the window and looked out at the California sunshine. Then he turned back to the class. "That's not a simple question," he said. "In fact, it might be one of the most complicated questions you could ask. Can you be more specific about what you mean by burn?" The student looked confused. "I mean, why does it hurt when fire touches your skin? Why does it destroy things? Why does it release heat?" Those are 3 different questions. Each one has a different answer. Which one do you want? "All of them, I guess." Feynman sat on the edge of his desk. "Okay, but first you need to understand something. When you ask why about anything in physics, you're asking me to connect it to something you already understand. If I can't do that, my answer won't help you. So let me ask you this. What do you already understand about the world?" The student thought for a moment. "I understand that things are made of atoms, that atoms have electrons and nuclei." Good start. "What else?" "That atoms bond together to make molecules, that molecules interact with each other." Excellent. "So you understand chemistry, at least the basics. That helps. Now I can answer your question in a way that might make sense." Feynman picked up the chalk. "But here's the problem. To really explain why fire burns, I need to explain what fire is. And to explain what fire is, I need to explain oxygen. And to explain oxygen, I need to explain molecular bonds. And to explain molecular bonds, I need to explain quantum mechanics. And to explain quantum mechanics, I need to explain probability and wave functions. Do you see the issue? You can't explain anything without explaining everything." Exactly. Every why question leads to another why question. It's infinite regression. At some point, I have to stop and say, this is just how the universe works, otherwise we'll be here forever. The student nodded slowly. "So what level do you stop at?" "That depends on what you're willing to accept as fundamental. For some people, God made it that way is where they stop. For others, quantum field theory is where they stop. For me, I stop at the Schrödinger equation. I accept that as fundamental and work from there." Another student raised her hand. "But Professor, can you at least try to explain fire, using whatever level you think is appropriate?" Feynman grinned. "I can try. But don't blame me if your brain hurts afterward." Feynman drew a simple diagram on the board. A carbon atom bonded to 4 hydrogen atoms. This is methane, natural gas, one of the simplest things that burns. Now watch what happens when I add oxygen. He drew oxygen molecules approaching the methane. The oxygen atoms want to bond with the carbon and hydrogen. Why? Because when they do, they'll be in a lower energy state. Nature loves lower energy states. It's like rolling downhill. Things naturally move toward configurations that have less potential energy. He drew new molecules, carbon dioxide and water. When methane burns, it breaks apart and recombines with oxygen to form CO2 and H2O. These new molecules are more stable than the old ones. They're at the bottom of the energy hill. A student interrupted. "But if burning releases energy by going downhill, where does the energy come from in the first place? Why was the methane at the top of the hill?" Excellent question. The methane was created by plants or algae millions of years ago. They used energy from sunlight to build complex molecules out of simple ones. Photosynthesis pushed the molecules up the energy hill. When we burn them, they roll back down. So burning is just reversing photosynthesis? In a sense, yes. Plants take CO2 and water and use sunlight to make sugars and oxygen. We take sugars and oxygen and release CO2, water, and energy. We're running the reaction backward. Feynman drew a graph showing energy levels. But here's the tricky part. Even though burning releases energy overall, it requires energy to get started. You need to break the initial bonds before new ones can form. That's why you need a spark or a match. You need activation energy. He drew a hump in the energy graph. It's like pushing a boulder over a hill. Once it's over the top, it rolls down on its own, but you need to push it up first. So fire is just a chemical reaction? Yes, a very fast chemical reaction that releases energy as heat and light. The heat makes nearby molecules react faster, which makes more heat, which makes even more molecules react. It's a chain reaction. A student in the front row raised her hand. But that still doesn't explain why it hurts when fire touches your skin. You're right. That's a different question. Let me address that next. Feynman erased the board and drew a simple sketch of a cell. Your body is made of molecules, complex proteins, fats, carbohydrates, DNA. These molecules have specific shapes that let them do specific jobs, enzymes that catalyze reactions, receptors that detect signals, structural proteins that hold things together. He drew heat waves approaching the cell. When fire touches your skin, it transfers thermal energy to your molecules. That energy makes them vibrate faster. When molecules vibrate too fast, their bonds break. The proteins unfold. The cell structures fall apart. That's what we call denaturation. It's what happens when you cook an egg. The proteins change shape permanently. They can't go back to their original form. A student asked, so fire hurts because it destroys our molecules? Partly. But there's more. Your skin has nerve endings that detect damage. When cells are destroyed, they release chemical signals. Those signals trigger pain receptors. The receptors send electrical impulses to your brain. Your brain interprets those signals as pain. So pain is just electrical signals? Just electrical signals? That's like saying Beethoven's Fifth Symphony is just air pressure waves. Technically true, but it misses something important. Pain is your brain's way of telling you to stop doing whatever is causing damage. It's a survival mechanism. Another student spoke up, but why does heat break molecular bonds? What's actually happening at the atomic level? Fire paused. Now you're asking the really deep question. To answer that, I need to talk about quantum mechanics. Are you ready? The class nodded, though several students looked nervous. All right, don't say I didn't warn you. Feynman drew two atoms on the board. When two atoms bond, their electrons don't just sit in fixed positions. They form what we call molecular orbitals. These are probability clouds where the electrons might be found. He shaded the area between the atoms. The electrons spend time between the nuclei, attracted to both of them. This shared attraction is what holds the atoms together. It's like two people holding the same rope. The rope is the electron cloud. Now, what is temperature? At the atomic level, temperature is just motion. Hot things have atoms and molecules moving fast. Cold things have them moving slow. That's it. Temperature is average kinetic energy. He drew wavy lines around the atoms. When you heat a molecule, you're making it vibrate. The atoms oscillate back and forth. They stretch and compress the bonds between them. If you add enough energy, the oscillations become so violent that the bond breaks, the atoms fly apart, the molecule is destroyed. A student raised his hand, but why do oscillations break bonds? What's the mechanism? Good. You're thinking like a physicist. The answer involves the potential energy curve of the bond. Feynman drew a U-shaped curve. This shows the energy of two atoms as a function of their distance. At the bottom of the U, the atoms are at their equilibrium distance. That's where the bond is most stable. When you add heat, you give the atoms kinetic energy. They can climb up the sides of the U-curve. If you give them enough energy, they can climb all the way out of the potential well. Once they're out, they're no longer bonded. It's like a ball in a bowl. If you shake the bowl gently, the ball stays in. Shake it hard enough and the ball flies out. Another student asked, but why does the potential energy have that U-shape in the first place? Why do atoms attract at some distances and repel at others? Feynman smiled. Now you're asking about the Pauli exclusion principle and the balance between electrostatic attraction and quantum mechanical repulsion. We're getting into territory that requires math, serious math. Are you sure you want to go there? The student hesitated. Maybe not right now. Smart choice. Trust me, the math gets ugly. Differential equations, complex numbers, probability, amplitudes. It works, and it predicts experimental results with incredible accuracy, but it's not intuitive. At some point, you just have to accept that this is how electrons behave. Feynman put down the chalk and sat on his desk again. Let me go back to the original question. Why does fire burn? I've given you several answers. Fire is a chemical reaction that releases energy. Fire breaks molecular bonds through thermal vibration. Fire triggers pain receptors by damaging cells. All of those are correct, but none of them are complete. Each answer raises new questions. Why do chemical reactions release energy? Why do molecular bonds break under vibration? Why do cells have pain receptors? I can answer those questions too. I can go deeper and deeper, but eventually I'll reach a point where I have to say, this is just how the universe is. The Schrödinger equation works. Quantum field theory makes predictions. We can verify those predictions experimentally, but we can't explain why the universe follows those laws instead of different laws. A student in the back raised her hand. Are you saying science can't really explain anything? That we just describe things without understanding them? Not exactly. Science explains things by reducing them to simpler things. We explain chemistry with quantum mechanics. We explain quantum mechanics with field theory. We explain field theory with symmetry principles. Each level gives us understanding of the level above it, but there's always a bottom level we can't explain. We can only describe it and verify that the description matches reality. So when someone asks, why does fire burn? What they're really asking is, connect this phenomenon to something I already understand. If they understand chemistry, I can explain fire in terms of molecular reactions. If they understand quantum mechanics, I can explain it in terms of electron orbitals and potential energy curves. But if they ask, why does quantum mechanics work that way, I can't give them an answer in terms of something simpler. That's where our current understanding stops. Another student spoke up. Does that bother you? Not being able to answer the deepest why questions? Feynman thought for a moment. Yes and no. It bothers me that we don't have a more fundamental theory. I'd love to understand why the universe has the laws it has. But it doesn't bother me that there might be a limit to explanation. Some things might just be brute facts about reality. What matters is that we can make predictions. We can build technology. We can cure diseases. We can send rockets to the moon. All of that works because our descriptions of nature are accurate, even if they're not complete. A student who hadn't spoken before raised his hand. Professor, can I ask a different kind of question? Go ahead. When you first heard the question, why does fire burn? What went through your mind? Before you started explaining, what did you think? Feynman laughed. Honestly, I thought, oh no, not another why question, because I knew where it would lead, down an infinite rabbit hole of explanations. But also, I was excited, because that question shows curiosity. It shows someone isn't satisfied with just accepting that fire burns. They want to understand the mechanism. That's the beginning of scientific thinking. So my real answer is this: fire burns because of a chain of causation that starts with quantum mechanics and ends with your subjective experience of pain. Each link in that chain can be explained in terms of the previous link. But the first link, quantum mechanics itself, we can only describe. We can't explain it in terms of anything simpler. Does that mean we don't understand fire? No. We understand it very well. We can predict exactly how it will behave. We can control it, use it, prevent it when necessary. But if you're asking for an ultimate explanation, something that doesn't depend on any prior assumptions, then no, I can't give you that. Nobody can. That kind of explanation might not exist. The original student who asked the question raised his hand again. So what should I tell someone who asks why fire burns? Like my little brother, who's 6 years old. Feynman smiled. Tell him fire is air and fuel combining to make new molecules that are more stable. Tell him this combination releases energy as heat and light. Tell him heat can damage molecules in his skin, which is why it hurts. Keep it at that level until he asks deeper questions. And when he asks why molecules combine, or why stability matters, or why heat damages tissue. Then you go deeper. You explain chemical bonds, energy states, protein structures. You match your explanation to his level of understanding. That's the art of teaching. The key is not to pretend you know more than you do. If he asks something you can't answer, say so. Say, I don't know, but let's find out together. That's more valuable than making something up. The student nodded. Thank you, Professor. Feynman stood up and walked to the board. One more time. Let me give you all one final thought. The question, why does fire burn, seems simple, but it touches on the deepest questions in physics. Why does the universe have the laws it has? Why does mathematics describe reality? Why is there something rather than nothing? We don't know the answers. Maybe we never will. But the fact that we can ask these questions, that we can probe deeper and deeper into the nature of reality, that's what makes us human. That's what makes science worthwhile. So keep asking why. Keep pushing for deeper explanations. But also recognize that at some point, the explanations stop. At some point, you just have to say, this is how things are, and work from there. And when you reach that point, don't be disappointed. Be amazed that we can understand as much as we do. Be grateful that the universe is comprehensible at all, because it didn't have to be. He put down the chalk. Class dismissed. The students filed out slowly, talking among themselves. Some were frustrated by the lack of a final answer. Others were energized by the depth of the question. The original student lingered by the door. Feynman was erasing the board. Professor, yes, I think I understand now. The answer to why does fire burn depends on what kind of answer I'm looking for. There's no single right answer. Exactly. Different levels of explanation for different purposes. That's the key insight. Thank you. I came in thinking it was a simple question. I'm leaving knowing it's one of the hardest questions you can ask. Feynman smiled. Welcome to physics, where the simplest questions lead to the deepest mysteries. The student left. Feynman finished erasing the board and looked at the blank slate. Somewhere in those chalk marks had been quantum mechanics, chemistry, biology, philosophy, all connected, all part of one grand attempt to understand why fire burns. And the answer, he thought, was both simpler and more complicated than anyone imagined. Fire burned because the universe was the kind of universe where fire could burn, where molecules sought lower energy states, where quantum mechanics governed atomic interactions, where human brains could experience pain. Why that kind of universe? Why those laws? Why anything at all? Those questions remained unanswered. Perhaps they always would. But that didn't make the search pointless. Understanding how things worked was valuable even without knowing why they worked that way. Feynman packed his briefcase and headed for the door. Outside, the California sun was setting. Somewhere in the distance, a fire was burning, releasing energy, breaking bonds, following the laws of quantum mechanics. Why? Because that's what fire did. And that, he thought, was both the simplest and the most profound answer he could give.